In our third example of finding where a function is increasing and where it's decreasing, we are going to look at this cube root function. It is f of x equals the cube root of 9 minus x squared. Now remember, the first thing we want to do is find the critical numbers or the critical points, which is involving the derivative. So we want to think about how we would find the derivative of this thing. Now whenever we have a cube root or any kind of root at all, and we're looking to differentiate, we do want to rewrite this with an exponent instead. So the cube root is the same as 1/3 power. Now this is a thing that we're going to need the general power rule on in order to differentiate, because we have some stuff raised to the 1/3, and it's more than just x to the 1/3. It's a function of x, or an expression of x raised to the 1/3 power. So the derivative of this function is going to be, well, we'll bring the 1/3 down in front. Okay, we leave the inside the same. Don't forget to subtract 1 from the exponent, so now that'll put us to the negative 2/3. And also don't forget, we've got to multiply by the derivative of the base, or of the inside. So the derivative of 9 minus x squared is negative 2x. So there is the derivative. We do want to use it now to kind of find where it's 0, find where it's undefined. So probably rewriting this will be helpful for us in terms of, using the derivative for a purpose. So we can always multiply the number here and the derivative of the inside together. So it'll just be negative 2/3 x, and then times 9 minus x squared to the negative 2/3. Then that negative exponent can go down underneath. We'll make its exponent positive. And up top, we can leave the negative 2/3 x. Another way that we could rewrite this is just bring this 3 down to the denominator with the 9 minus x squared, and leave the negative 2x up top. Either way is fine, we'll get to the same answer. I don't know, I think that this way is a little nicer to look at, so I'll use this, this representation. Okay, so we want to go ahead and find the critical points for the critical numbers. Right, these are the possible places where the original function could turn around or change its increasing or decreasing behavior, switching from one to the other. So where there are two kinds of critical numbers, the first is where the derivative is equal to 0. So we want to set this whole derivative expression, the negative 2x over 3 parentheses 9 minus x squared to the 2/3. We want to set that whole thing equal to 0. Now this looks like it's going to be a kind of crazy thing to solve, but remember that when you've got a fraction set equal to 0, you can just cross multiply, and what ends up happening is that the denominator just goes away. So if you multiply across to this side here, or multiply both sides by the denominator, that's going to cancel it here, and then over here we'll just get 0. And when we divide by negative 2, that gives us a critical number of x equals 0. All right, that is 1/2 of our critical numbers, or at least 1/2 of where they can come from. All right, the other half is where the derivative is undefined. This does apply in this case because our derivative has a denominator. So again, this is where the denominator of the derivative is 0. That would mean that we don't have a slope because we've got an undefined value when we divide by 0. Okay, so we're just going to set the denominator itself. Just set that whole thing equal to 0. I want to solve this for x. It looks kind of complicated, but once we start just getting rid of some stuff, like we could divide by 3, we could divide by 3. That actually just simplifies the left side, but leaves the right side at 0. We've got 2/3 power on the left. To get rid of that, we could raise to the 3/2 power. because when we multiply powers, or when we raise a power to a power, we end up multiplying those powers. And if we multiply 2/3 by 3/2, we get 6 over 6, and that's just 1. So these essentially cancel out. And on the right-hand side, that's still just 0. So essentially what we have here is that if you have a constant times some stuff raised to a power, the only time that that's going to be 0 is when the stuff that's raised to the power is 0, right? That's what this is saying here. And that should make sense because you can't raise a number to a power and get 0 out unless the base is 0. So this is a difference of 2 squares, so we can factor this into 3 plus x times 3 minus x. Okay, that gives us x equals -3 and x equals +3, 2 more critical numbers. Okay, so it looks like we found 3 places where the function here could turn around. We do have to kind of determine, where the function is going up or down. So this is where we make a sign chart for the derivative. Okay, so we make a fancy number line, and we're going to put our critical numbers in order from left to right. So we've got -3, we've got 0. Actually, I'm going to make mine bigger this time just because we've got so many intervals here. So we've got -3 first, then we've got 0, and then +3 is the bigger one. All right, so we've got 4 intervals here. We've got -infinity to -3. We've got -3 to 0. We've got 0 to 3. And we've got 3 to infinity. All right, so what we want to do here is carefully test some points that live within each of these 4 intervals. So we pick some test values. So we're going to pick, how about x equals -4. And remember what we mean by test. I mean, we're checking the sign of f prime on each interval. And remember, again, this works because we have found the possible places where the sign might switch. So at all x values within each of these intervals, the sign will not switch. The sign will not change. It'll be the same. So we just pick a nice convenient point. Like how about -4? We're plugging that into the derivative. So we'll have -2 times -4. And that's divided by 3 times 9 minus -4 squared to the 2/3. Oh my gosh. So really carefully plug this into your calculator. Let's see, up top, we'll get a +8. Down bottom, 9 minus, okay, -4 squared is 16, so 9 minus 16, that's -7. And then we're raising that to the 2/3. And remember, 2/3 is power over root, so we're squaring, and then we're taking the cube root. Or we're cube rooting, and then we're squaring. But in either case, we're squaring, and that's going to turn the denominator around to be positive, because when you square something, you always get a positive thing out. So this is going to be positive over positive. So I can tell without even plugging this into my calculator, this is just going to be a positive value. And remember, we don't care about the number. We just care about the sign. So go ahead and test some other values here. If you have troubles with plugging things in your calculator and you just can't figure out how to do it right, I can help you. There are some tricks. You could put in the derivative function into y1 and y equals, and then you can go to your table and see what the y values are in that way. It could be a little easier. But if you only have a scientific calculator, you've got to just kind of be good at plugging some stuff in, unfortunately. So let's see. So -2 times -1 over 3 times 9 minus -1 squared to the 2/3. Up top, that's +2. Down bottom, this will be 8 to the 2/3. Everything's positive there. So again, this will just be positive. All right, between 0 and 3, how about +1? So we'll say f prime of +1. So it's -2 up top times x, so -2 times 1, over 3 times 9 minus +1 squared to the 2/3. All right, up top we'll have a -2 this time. Down bottom we'll have 3 times 8 to the 2/3. Now I know like we could simplify this further, but again, all we care about is the sign. So it'll be negative up top and a positive down bottom. So when you divide those overall, that number will be negative. All right, last, we got 3 to infinity. So let's test x equals, how about 4? So we're going to plug in a 4 into f prime. We'll have -2 times 4 up top. Down bottom, we'll have 3 times 9 minus 4 squared to the 2/3. Up top, we'll have -8. Down bottom, we'll have 9 minus 16 again, so that's -7 to the 2/3. And again, we're squaring that down there. It's power over root 2/3. That'll be positive, and then we're cube rooting that. It's not going to be like a whole number or anything, but it will be positive. Wait, positive down in the bottom, negative up top. So negative over positive gives you negative. Okay, so let's make our conclusion, and then let's fingers crossed check our work that this came out to be good. Okay, so these things in these boxes here are like the essential steps. So f of x, the original one, which was the cube root of 9 minus x squared, right? It's increasing on negative infinity to -3, also -3 to 0, and then it's decreasing on the after 0. So 0 to 3, but the derivative was undefined at 3, so we can't, mush those together. We just say union 3 to infinity. Alrighty, I think it is time to check our work. So why don't we do that? I'm just gonna set up my graph here. So here's the y-axis and the x-axis. Okay, remember we're gonna graph the original function. So that'll be the cube root of 9 minus x squared. Okay. So again, take out your graphing calculator or pull up Desmos. It is an app, I believe, but it's also a website. It's free. And we want to do the cube root. I see a square root, but I don't see cube root, so I'm just going to do the 1/3 power. If you put this in your graphing calculator, when you put in the caret to do an exponent, if you're going to type it in that way, make sure that you put the 1/3 in parentheses. If you don't have one of those calculators that puts it up in the square for you in the exponent place, because if you don't do that, then the divided by 3 won't be considered to be in the parentheses. So just to be clear, you want to do it like, so 9 minus x to the second, and then to the parentheses 1 divided by 3, if you're putting that into a TI-83, I guess. So here we go. Here's, oh, it's so cute. It's kind of weird, but it's, I don't know, almost like a hill of some kind, except it looks like at -3 and +3. Let me just get rid of this. That was where we had our undefined derivatives. And you see what's going on here? We have some vertical tangent lines. So we don't have a slope at those points, but the function does increase to the left of -3 and from -3 to 0. And then it turns around and decreases from 0 to 3 vertical at that point. And then from 3 on, it continues to decrease. So it looks like we did a good job. Let's just sketch that in. Okay, so let's see, we've got -3, 0, and 3. And the graph looked something like this. So there's the graph of that function. Right, we found that it was increasing from here to here. We got a vertical tangent line at -3. It's increasing still from -3 to 0. Then it turns around and starts to decrease. At 3, we have undefined slope of vertical tangent line again. But then after 3, it decreases again. Okay, so I don't know, I think this function is really cool. I still, doing these after all these years, still think this is really just an amazing thing we can do. So I've got one more example for us to look at with this, so tune into that if you'd like, and I will see you then.